Hello and welcome to this video on how to use single indicators in CFA and SEM. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate methods including factor analysis, structural equation modeling, multi-level analysis and latent class modeling. If this is something that interests you, please subscribe to this channel. Also, check out the description for additional resources, including workshops that I offer through QuantFish. In this video, I want to show you how you can use single indicator variables as measures of latent variables in CFA and SEM. What you're probably most used to seeing is a model like this, where we have multiple indicators, in this case 3 indicators per factor, and here in this very simple latent regression model, factor 1 predicts the factor F2. However, in certain situations, you may not have multiple indicators available for each factor. Maybe you have only a single indicator. Maybe you have only a single item measure for measuring one or the other factor. And then the question is, what do you do? Now, one approach would be to use a path analysis or regression analysis with single indicators. But the downside of that approach is that then you have no correction for measurement error in the exogenous or predictor variables. So what would be more desirable in the case of single indicators is a model like this, where you have one indicator per factor, but you still have a factor in each case, and you have error terms at the bottom, epsilon 1 and epsilon 2. So the question is something like this also possible? And that's what I want to show you here in this video, how this works, how you can set this up. And I will also show you an example, and then at the very end I will talk about some caveats and potential mistakes that you could make that you have to be careful about. So let's get started, and let's take a closer look at the model on the right hand side here, the model with single indicators, and let's see how and when and under which conditions something like this could work. So first of all, we need to talk about what parameters are free parameters in this model, meaning what are unknown parameters that we want to estimate. And so in this model, we would want to estimate the variance of the first factor, the path coefficient or regression slope coefficient for the linear regression, in this case of F2 on F1, and then also the residual variance for the residual R2, because F2 is explained in the model, so it has no variance parameter, but it has a residual variance parameter. And then in addition to that, we also have for the measurement portion the 2 epsilon error, measurement error variances that are that we need to estimate. And you can see factor loadings we don't have in this model because those are fixed to 1. When you have only one indicator, then you need to fix that loading to 1 for identification. Otherwise, this wouldn't work at all. So can this work with those 5 free parameters that I listed here? In order to think about that, we have to think about what pieces of information can we use in a structural equation model to estimate free parameters. And when we only consider the covariance structure here for simplicity and leave out the mean structure, which is typically not of interest when you have cross-sectional single group data, then the only information that we have is the covariance matrix with the variances in the diagonal and the covariance off diagonal. So in the case of 2 variables, we have 2 variances in our data, and we have 1 covariance between the 2 variables. So those are the only pieces of information that we can use to estimate model parameters. And so obviously here we run into a problem, because in blue you can see we have 5 free parameters in our single indicator SEM model. However, we only have 3 pieces of information in our data. So this would mean the model would be under-identified, or we could say it would have negative degrees of freedom, because 3 minus 5 equals -2. So this model has negative degrees of freedom and is under-identified. So we have too many parameters. Now, how can we solve this issue? So the key to this is the measurement portion of this model. So we need to take away those measurement error variances, variance epsilon 1 and variance epsilon 2, on the side of the free parameters. Now, obviously, we could fix them to 0, and then what we would have is a manifest path model or a manifest regression model, because then we would assume that there's no measurement error variance, that all the variance in our observed variables y1 and y2 is true score variance, and then this would be equivalent to a manifest regression model or a manifest path model. And that's not what we want. So instead, what we want is we want to make use of an equation that we know from classical test theory. And so if you're not familiar with classical test theory, please check out my videos and playlist on classical test theory on this channel. I also offer a course on classical test theory through QuantFish, in which I discuss these things in detail. Here I only want to point out that one fundamental equation in classical test theory is that the variance of an observed variable is a function of true score variance, in this case reflected as the factor variance plus error variance, variance epsilon. So the variance of an observed variable can be additively broken down. And a basic assumption or idea in classical test theory is that scores contain measurement error typically. Now, there may be the situation where you have perfectly reliable scores in principle, so that theoretically is possible that there's no measurement error variance. However, in practice, it's usually not plausible. So usually there is a measurement error variance component. And so then the question is, how can we estimate that component from so little data, or where could the information come from? And so for that, we can make use of another equation or another law from classical test theory, and that is that the reliability of an observed variable is equal to the variance of the true score variable for that variable divided by total variance, and that's equal to 1 minus the error variance component divided by total observed variance. So this is another equation that follows from classical test theory, and so we can make use of that equation because we can solve this equation for variance epsilon. And so when we do that, then we obtain variance epsilon equals the variance of our observed variable, observed score, times 1 minus reliability. So in other words, if you know about the reliability of your score, then you can estimate the epsilon variance, and then you no longer have to use this as a free parameter in the model on the left hand side, but instead you can fix it to that value. And that's the trick that we're using when we are using single indicator models in CFA or SEM, because in our data, we do have the variance, we have that covariance matrix, so for each variable we have the variance, we can calculate that from our data, and then we also may have a reliability estimate that we have come up with in one way or another, and I'll talk about that in a little bit, how you would come up with that reliability estimate. But that's, so to say, key to single indicator models, is that you need to have an idea about the reliability of your variables, and then you can use that information to calculate the error variance component from your data using this formula that is given here at the bottom. So that's the key formula to resolve this identification problem of the single indicator model. So now let me show you an example so you can see what that would look like in practice. So here in this example, I have a predictor variable that is spatial abilities, and my dependent variable here is the math score, math achievement. So I'm trying to find out whether individuals with higher spatial abilities also have higher math achievement, and so I'm using spatial abilities here as a predictor, and I have a single score for spatial abilities, that's y1, and I have a single score for math ability, that is y2. Now, I did a little work here with SPSS in this case, and so for spatial abilities I found out that the variance of y1, so this scale score for spatial abilities, has a variance of 22.19 in my data, so that's var y1. And I also found out that Cronbach's alpha for my spatial ability scale is 0.79. So that's my reliability estimate, which in this case applies to this scale and which I'm going to use in the formula that I just showed you to estimate the error variance component. So using that formula, then I obtain 22.19, that's my variance, times 1 minus reliability, 0.79, equals 4.660. So this is the error variance estimate, so the estimate for the variance of epsilon 1. And now I did the same thing also for the math score. I figured out using SPSS that the variance of that scale is 32.454, and in this case McDonald's omega was used for reliability estimation since this is a congeneric scale. And so McDonald's omega here was 0.815. Cronbach's alpha would have been a little too low for this scale, would have been around 0.8. And so here McDonald's omega was more appropriate. Again, using the variance estimate for the scale and McDonald's omega reliability, the coefficient omega, and then this formula, I obtained 32.454, the variance, times 1 minus reliability, 1.815, and so the error variance component for the second scale is then 6.004. Now, these are the ones that you want to use in your model. So when you set up this model in, for example, Mplus or in Lavaan or something like that, then the error variances must be fixed. And I'm going to show you this next, how this is actually done. So here we have the Mplus model statement. The model statement in Lavaan would look very similar. And so you can see that I have my factor 1 set up with a by statement, MRT sum. So that's the mental rotations test. That is a measure of spatial abilities. Here is the indicator, and it has a loading fixed at 1. It's a single indicator. And then MRT sum, its error variance is fixed at 4.660. That's the value that we just calculated with the formula from classical test theory. And so in Mplus, when you specify the name of an indicator variable again, then that automatically refers to that variable's error variance, since the variable is an endogenous or dependent variable. It depends on the factor here. And then the same principles apply to the second factor, which is the math sum score. Again, the loading of the single indicator is fixed at 1, and the error variance parameter is fixed at 6.004, so that Mplus doesn't have to estimate those two error variances. And then finally, we have the structural model. F2 on F1 means the math factor is regressed on the mental rotations or spatial ability factor, and that's our latent regression coefficient that will give us here the beta 2,1 estimate. Let's take a look at some of the output as well. So I'm not showing you the entire Mplus output, but only selected parts of it. And so you can see here the unstandardized estimates, and you can see what was estimated was the beta coefficient 0.407. So that's our unstandardized regression coefficient with a standard error and a z-statistic for a test of significance, and the p-value is 0.000 something, so the coefficient is significant at the 0.05 level. Also, Mplus estimates the variance of the factor 17.477, as well as the residual variance of the second factor, which is given here below as 23.483. Notice that the residual variances are also given for the indicators, however, those are fixed. And you can see that from the fact that they have no standard error, and that you get the 999s here printed for the significance test and p-value, because those are fixed parameters. They're not estimated, and therefore they have no standard error and no test statistics. So really the only three free parameters in this model are the regression coefficient, the factor variance of the exogenous factor, and the residual variance of the endogenous factor. Those parameters are freely estimated, and therefore they also have a standard error. Furthermore, you get standardized estimates as well as you would for a multiple indicator model. So in this case, this would then be the standardized regression coefficient 0.331. And again, it's significant. You can see that here from the p-value. So there's a significant linear relationship between the math factor and the spatial ability factor. We also get R squared when we ask for the standardized solution, and the R squared values for the observed variables here correspond to the reliabilities. And so you can see within rounding error, we get the 0.79 for the spatial ability score and the 0.815 reliability coefficient for math sum. So that's a good way to check that you calculated your error variances correctly with this formula, because those reliability estimates here should make sense. They should converge with the ones that you used in the formula. Otherwise, you may have made a mistake when calculating your error variances. So this is a good check. And then also we get the latent variable R squared for our endogenous factor, which here is 0.110. So 11% of the latent or true score variance in math score or math ability can be predicted from the spatial ability factor. Now, there are also some caveats when using the single indicator approach, and then obviously, or the most obvious potential problem is that the reliability estimates may not be appropriate. So, because the question is, how do you come up with those reliability estimates, right? And so in my case, I used appropriate statistics, Cronbach's alpha for the spatial ability scale, and I used McDonald's omega for the math scale. Those were appropriate because I tested the relevant measurement models first for the spatial scale and for the math scale, and those were the ones that should be used. However, this is also kind of silly, because if I'm using those statistics, then why not use multiple indicators to begin with? So the spatial ability scale to which I applied Cronbach's alpha for a tau equivalent measurement model consists of 2 subscales. So I could have used those 2 subscales as indicators. And then for the math test, I have 4 subscales, and for those the congeneric measurement model applied, and therefore McDonald's omega. So I could have used those 4 scales as indicators in an SEM. So there was really no point here in this example in doing this as a single indicator model. Really no reason to do it. I could have done multiple indicators. And so in many cases that is the case, that you have multiple indicators. And so why would you even do that? So it really only makes sense if you have just one indicator. And then the question is, where does the reliability estimate come from? And so sometimes you may be able to derive that from the previous literature. However, then the question is, does it apply? Because a reliability statistic is a sample dependent statistic. And so when you have a different sample with different variability, then your reliability coefficient may be different. Also, who knows if previous studies used a reliability coefficient that made sense? Many people just simply apply Cronbach's alpha to whatever scale they have, and so maybe that actually didn't really apply to their scale, and therefore is maybe an underestimate of reliability. And then what happens if you underestimate the reliability and you overestimate the error variance component? As a consequence, then you have an overcorrection of your path coefficients, or a bias, so to say, in estimating your path coefficients, and so that can be problematic. So you want to make sure that you have reliability estimates that are accurate, that apply to your specific sample. And so you want to be very cautious when selecting reliability estimates to make sure that they really apply to your single indicators. A good idea here is to do a sensitivity analysis to make sure, or to try out different reliability values if you're not sure, to see how that influences your structural coefficients, your path coefficients, and other values in the structural model. Also, some people say really what you should use is not reliability but validity. So you should make a correction in terms of the error component, in terms of validity. So you really want to have the valid portion of variance that is used here, because the reliability could contain method variance, it could contain multidimensionality if the variable measures multiple factors, and so on. But that's then even more difficult, because coming up with a proper validity estimate is even more difficult than coming up with a proper reliability estimate. But that's another issue to consider when using single indicators. And then finally, I already mentioned that oftentimes there's no need to do this because you do have multiple indicators. So for example, a scale might consist of multiple items, and you may not have to use the scale or the item sum score, but instead you could use items as indicators, or test halves, or item parcels, or something like that. Now, this comes with its own set of problems, but it's always worth considering whether you really need to use a single indicator SEM model or whether you could use multiple indicators. Now, a single indicator model typically you would have to use if there really is only a single indicator, meaning, for example, if it's a single item measure, which we sometimes have. Sometimes, for example, in online surveys, life satisfaction may be measured with only one item that says, how satisfied are you with your life on a scale from 0 to 10? And then there's no other measure. So then in that situation, you'd have to rely on a single indicator SEM, and you'd have to come up with a proper reliability estimate. However, in many other situations, when you have multiple item scales, then you can come up with a solution typically where you use multiple indicators rather than a single indicator. I hope you found this video useful to learn about how to use single indicator variables in CFA and SEM. If you did, please subscribe to this channel. Don't forget to check out the description for additional resources, and I'll see you next time.